Hi everyone. Today I'll be presenting on a paper called Exact Conversion of In-Context Learning to Model Weights in Linearized Attention Transformers. I'm Brian, and this paper is written with Tianyang, Xinhui, Huiquan, and Kenji. So let's get down to it. I'll first start by introducing large language models. I'm sure everyone here is already familiar with them, but I'll just go into them anyways. So with the release of GPT-3, large language models have gained a great deal of popularity, with many different companies and organizations building their own. And they're now being used in multiple different industries, including medical diagnosis, virtual assistants, and sentiment analysis. And what makes them so interesting is as large language models grew in size, new abilities called emergent abilities also appeared. One such ability is in-context learning. So what exactly is in-context learning? Well, in-context learning involves learning to generalize and make predictions on new tasks based on demonstration examples provided in the prompt. It allows us to incorporate information into the model without additional training. But I'll give some real examples, right? When we go up to someone, a language model, and ask, "What is my name?" it won't know, right? However, when I provide context and say, "My name is Brian, what is my name?" all of a sudden, the model knows that I'm called Brian. Now, as a human being, this is very intuitive because it's how conversation works. But for machine models, this is incredibly weird because without gradient descent or any training methods, we've effectively given the model information that my name is Brian. So what exactly are the strengths and weaknesses of this new way to impart information on a model? Well, the strengths are evident. First of all, it doesn't require training the model weights. That can be extremely expensive, especially on the newer ones which have 70 billion parameters or I'm gonna guess. They get very large and training them is costly and very power hungry. So another benefit of in-context learning is it's extremely interpretable. Just as in my example, the demonstration is typically performed in the form of natural language and is readily understandable to us. However, it also comes with a trade-off compared to traditional fine-tuning and machine learning. First of all in-context updates are temporary in nature. If I don't include the in-context learning prompt in future inputs, the information is no longer retained. And appending in-context prompts increase the computational cost while decreasing the training cost. And this is a big issue because the computational cost increases quadratically with length. So a quick example, if my context is 90 words and my prompt is 10 words, I've effectively increased the cost of computation 100-fold, which is a big issue. That brings me to the focus of our work, which is to find a way to permanently encode ICL prompts into the network weights. This way, we can get rid of the issue of added computational cost and hopefully get the best of both worlds. In our work, we show that this is possible, an exact conversion is possible in the case of linearized transformers, while we can achieve an approximate conversion in the case of regular vanilla transformers. And we experimentally show the effectiveness of our results as well. So now let's get into attention in transformers, something I'm sure almost everyone viewing this video will know to a certain extent. So attention is the fundamental building block of the transformer, and we ascertained that if you can achieve conversion within the attention block, that's all you need to do, because most other things are element-wise and are not a problem. So attention can be understood as the following equation, and that's the equation which we will be focusing on. It's the form found in multiple works, such as the ones by Cathropoulos, where here sim is a similarity function. So here, let's get into it. we can observe the attention equation here, which I highlighted previously. It has an input, x, which is a sequence of tokens, and this is then transformed linearly into the query, key, and value matrices. As mentioned, sim is a similarity function, which is actually the bipartite exponential function, but I won't get too far into it. Now, a popular way of transforming the attention equation is to change it into linearized attention. This involves approximating the similarity function by a kernel. While it's not exact, it allows us to reduce the computational complexity to linear time. Of course, there is trade-offs such as performance, but it is still a very interesting direction to go. So what happens when we include in-context learning prompts? Well, this means the inclusion of another separate sequence of tokens. Here we'll call it x prime, and the equations we previously mentioned become as follows. Notice that there's an additional term, which I've highlighted in red here. And the idea is when we add the in-context prompts, the attention transforms into these following equations. Then our idea is simple. Since we know that in-context learning is captured in those terms highlighted in red, we can simply save those terms as bias terms instead of carrying out the equation each time. Notice that we can achieve an exact conversion in the case of linearized attention. However, when we go to regularized attention, we still need to we basically need to linearize the portion which we want to convert, and we approximate that with a linearization, since it's not possible with regular attention. While this isn't perfect, it does give us an approximation which we found can achieve a degree of effect. For the exact form, here's the theorem in our paper. We note that there are two things to highlight here which are interesting. First of all, inclusion of a BKV prime over BKV means that we think you can extend in-context learning prompts and keep adding to it through our method. The second thing is the inclusion of the rotary positional embedding, which we consider important because it's not a fixed positional embedding. Here it takes the form r theta. So in actual practice, how is the bias calculated? Well, you first pick the specific context prompt which you're interested in, and you pass that context prompt through the entire model just a single time as a forward pass. And at each layer, we can use our formula to calculate the bias. So it is an extremely cheap procedure, assuming that you already have the kernel which you want. So now that we have the theory roughly down, let's get into experimental results. We start with linearized transformers. We basically took a simple linear transformer architecture and we randomly generated the weights of the model. We then checked how accurate our conversion method was as we scaled up the number of weights. And we find that the conversion is almost exact, and any error there is can be attributed to the fact that Python is not exact and has an error to a certain number of decimal points, which we think is fine. And as you can see here, even as we achieve billions of parameters, the error still stays extremely small. We then performed a test on a toy case to see whether the ICL is actually capturing the in-context information. This is a toy case with linear transformers where the model can takes in sequences of randomly generated letters. However, after specific letters, specific trigger letters have to be followed by another letter. For example, maybe my choice is that all F's have to be followed by the letter U. Now, if you don't tell the model this, it has no information, and it's going to randomly generate the next letter. However, if you do tell the model, it'll get that right every time. So we find that the original model, with in-context learning, has an accuracy of essentially 100%. However, if you don't tell it which triggers there are, the model completely screws up. With addition of our in-context term, however, we revert back to nearly 100%, which makes us believe that we can capture in-context information almost exactly for linear cases. While linear models are extremely interesting, we do note that regular models, most models are still built on the regular attention model. So we decided to carry out an experiment on GPT-2 because it's relatively simpler and we're doing this more as a proof of concept. We used our approximation method to attempt to include context into the model through the addition of biased terms. We acknowledge that it's not exact, but we do have real evidence that it works, but to an extent. So let's get into that. So let's start with a model, an example, right? A concrete example which is readily understandable. We start with the prompt, Bill Gates was born in Seattle, Washington. He is the CEO of. And here, if you observe, it gives us a very detailed understanding that Bill Gates was born in Seattle, and it tells us some of his information. And when we include our bias terms and just ask he is the CEO of, the model still does fairly well. It still knows that we're talking about Bill Gates. It still mentions that he is the CEO of Microsoft. However, without our bias term, if you just ask he is the CEO of, the model has no way of knowing that we're talking about Bill Gates. And it thinks we're talking about the CEO of a European cryptocurrency exchange. So here, while our bias term hasn't achieved exact conversion, right? The outputs are different. The model has retained the information that we're talking about Bill Gates. The second example I'll provide is the in-context prompt about Los Angeles. And the full sentence is, Los Angeles is the second most populous city in the United States. It is in the state of, right? And the model tells you that's in California, and it has information about Los Angeles. When we include our bias term, and we just ask, it is located in the US state of, the model still knows that we're talking about Los Angeles because it outputs that we're in the US state of California. I'm going to say that if you just generate it at random, the chance is probably somewhere around 1 in 50, right? However, and if we don't include our bias term at all, the model has no idea that we're talking about California or Los Angeles, and it outputs that it's in the US state of Texas. So once again, we've achieved teaching the model that we're talking about Los Angeles. Now, I think it's important to highlight that these examples are cherry-picked to an extent. However, we cherry-picked not to find the best cases of conversion, but rather because GPT-2's performance is very limited, and in some cases, we couldn't get the initial sentence to work at all. So I would like to highlight the cherry-picking, but mention that the bottleneck here wasn't the conversion effect. Why is this important? Well, we think that permanent ICL forms a realistic alternative to existing weight update methods. And if achieved on an almost exact level, even for regular transformers, it won't just be a side grade, but be an upgrade in many cases, because it'll make LLMs easier to modify for general users, and it will help democratize the technology. Small businesses will be able to train, in a sense, large language models without the very, very hefty costs which comes with it. And we think that the significance of this work will only grow as LLMs grow further in popularity and as kernel research grows and improves, which will help us make our approximation method even more accurate and will make linearized transformers even better. Future work we want to explore includes finding more specific kernels to make our approximation even more accurate and building network architectures to properly take advantage of in-context learning. Thank you very much for your time. I hope you found it informative.